Thank you, Professor Sérgio Ferreira, and the organizers for the invitation. The model of semiconductor for proteins has about 70 years, several decades. Then here we will use this model to explain some phenomena of quenching, of fluorescence quenching in proteins. The absorption of UV light in tryptophan conduces to several de-excitation processes that compete with fluorescence. And then the quantum yield here is minus 30%. In some cases, the fluorescence disappears totally. The absorption of light of tryptophan has two main contributions in the spectral UV spectrum. The LA, that is the transition from HOMO to LUMO, and LB, that are two transitions, one from HOMO -1 to LUMO, and another from HOMO to LUMO +1. Here we are investigating the chemotrypsin inhibitor protein that is completely that loses completely the fluorescence emission when folded. And then the question in his work is why, to try to answer why. We will use molecular dynamics with hybrid methods that treat the main interest region using quantum mechanics, and the rest of the system, classical mechanics. Here we introduce all the protein in the quantum mechanics part. The protein has 63 amino acids, about 1061 atoms. In the molecular mechanics region, we put the rest of the system, the water molecules and the ions, in a box of simulation. What we observed is that the HOMO and HOMO -1 is most part of the time in the indole group on the tryptophan. And the LUMO and the LUMO +1 travel to several parts of the protein, mainly in positive charged parts, positive charged residues as arginine and lysine and N-terminus. And then we can see 1 picosecond of molecular dynamics using the hybrid methods. Most of the time, HOMO and HOMO -1 is over the indole moieties in tryptophan, and the LUMO and LUMO +1 was stood around. And then the question is how the transition can reach the LUMO and the LUMO +1, because the transition is in the vertical. According to Frank Condon principle, electron transition in molecules must occur vertically. And then the electronic state above the first two excited states above the indole is LUMO +7 and LUMO +19. And then what happens is after the light absorptions, the electrons can go back to the HOMO and the HOMO -1, emitting fluorescence, or transfer energy to normal modes of vibration at the structure, going from orbital to orbital, losing these energies until reach the LUMO orbital. And the LUMO and the LUMO +1 in the protein, as we see in that video, are over electron acceptor residues, the H1 in this case, that is a positively charged residue. The intermediate states will be distributed between the LUMO and the LUMO +1 and the LUMO +19. The rest of the states. What is interesting is that low energy unoccupied orbitals tend to be around the electron accepting residues, Rg+. In this region here, we have some images of these orbitals. And the energy difference between these orbitals is about 0.3, 0.4 electron volts. Is the same energy of the vibration spectrum in organic molecules in the same region, 0.2 to 0.3 and something, almost 0.4 electron volts. And then what happens is that the vibronic states interconnect one to another, and then as a efficient way to dissipate the energy. What happens with the higher energy unoccupied orbitals is that they tend to surround the electron donating region or spread out along the chain. Here we have some picture of these orbitals. They tend to localize or unlocalize, spreading along the chain. The emission of tryptophan is mainly due to the LEA state. At the higher density, you have a high density of the states because the states approach one to another. Above the LEA states here in LUMO +7. May facilitate the non-radiative excitation from the first LB state of the tryptophan. Then we have something like a band of energy, like in a semiconductor. Two discrete mechanism has been described in the literature. In this case, this mechanism describes the electron transfer process that changes as a function of donor bridge acceptor. The mechanism tends to lose the efficiency as the distance of donor from acceptor enlarged, but in the same time, the lot of electronic states accumulates in this place, and then the energy between states decreases. The two mechanisms are hopping and tunneling. When donor is the donor of energy is higher energy than the one of bridging peptide, the electron hops between low energy sites. The energy sites is the peptide bond, and then the electron after the light absorption and goes hopping from one bond to the other, one p bond to the other. But when the energy of the donor is lower than the energy of the barrier along the chain, the barriers, then the electron tends to tunnels through the bridge to reach the acceptor. In some cases, when all of the electrons' energy is transferred to vibrational modes along the path, it may not reach the acceptor. For the helix peptide, we have a similar picture. Here, the electron can cross the chain and can be transferred in a kind of a wire using the hydrogen bonds. And also for helix structure, the vertical electron transitions often occur to the first unoccupied orbitals above the LUMO and the LUMO plus 1. That are the first states over the IDOR to maintain the spectral range observed experimentally. Then experimentally, the range of the absorption is from 250 to 190. And then to maintain its energy, the first state will be far from the real LUMO and LUMO plus 1 of the protein. For these peptides, an arginine with 19 glycine in a helix conformation, the indole first excited orbitals are LUMO plus 14 and LUMO plus 23. Like in beta peptides, the remaining orbitals must be accommodated below the LUMO plus 23. Also, in this case of helix, the lower energy occupied orbitals tend to be around the electron donor, the electron acceptor residue here, arginine, that has a positive charge. Then here, the lower energy orbitals. And like beta sheet peptide also, the higher energy unoccupied orbitals tend to surround the electron donating region or spread out along the chains also. In general, the energy difference between states are about 0.2 to 0.3 electron volts in the region of vibrational spectra of organic molecules, chemical bonds in organic molecules. And then the vibronic orbitals can interconnect. Most of the orbitals localize over 3 or more residuals. Here we put the here now you have 3 or more residual with the same orbitals, the same orbital. The electron transfer mechanism can be hopping or tunneling, like in beta sheet peptide, but also through the hydrogen bonds in backbone. As a general mechanism, we have when thermal relaxation reach the AEA state, there may be fluorescence or continuity of energy conversion to the vibronic state. And then here we have the point of decision. If the electron reach the LEA, then we can have fluorescence. Or if it's taken another way, it is will be transferred the energy successively until reach the LUMO orbital. Since there is no possibility of fluorescence emission of the remaining energy from the LUMO that is over the arginine residue, the electron cannot reach the tryptophan, the HOMO or HOMO -1, where is a lack of electron. There is no orbitals in arginine in ground states that can receive its electron by fluorescence emission. And then the emission is again by thermal relations. And then the thermal relaxation must continue until the electron returns to HOMO or HOMO -1 over tryptophan, ending and then the cycle. This could explain the low or zero quantum yields of some proteins. Then here we have the key moment. The electrons can go to the LEA orbital and emits the fluorescence, or lose the energy to the transfer the energy to the vibrational states along the peptide until, or the protein until reach the LUMO orbital. And here the laboratory in the Institute of Biophysics at the Federal University of Rio de Janeiro. Then the staffs. Thank you.
Questions to Pedro?
Hi, Pedro. Very nice talk. Thank you. So we've been through this a few times, but I'm not a physician. I mean, not a physicist. I'll just ask this once more and see if I can understand this once and for all. You said that the Frank-Condon rule states that the excitation must happen vertically, but it does not say that the de-excitation must do that. So that's why the electron could, dissipate the energy horizontally. Is that it? Did I understand correctly? I mean, I'm a biologist, so yeah, you have to forgive me.
For the non-radiative relaxation, there is no rule, and then it can go transferring the energy in several senses, every time decreasing the energy and transferring the energy to the normal modes of vibration. But in Frank-Condon principle, the movement is fast. It's very, very fast, and then the light is absorbed in femtoseconds, and then it reaches only the states on the part of the chromophoric parts of the molecules.
So, Pedro, just one quick idea here. If I understood correctly, you think that this protein is highly quenched because the LUMO is not on top of the tryptophan where it should be, but rather on top of the arginines. Now, what if you do a simulation in which you mutate those residues to non-charged? Because I assume this is a pi-cation type of interaction between the indole and the arginine. So what if you mutate those two amino acids and then presumably you would block this LUMO from sitting on top of that? Would then you predict an enhancement in quantum yield?
Yeah, so we did with Gerson Labs some mutations, and the fluorescence even was quenched. But there is a lot of charged residues, and then a multiple way to quench it. And then I think the key point is that point that the orbitals approach the electron donor, the density of orbitals near the IDOR can transfer fastly the electrons, and they cannot be back to our orbitals that can fluoresce, the LEA orbitals. And then I think that the transfer is fast because of the surround of the donor is very efficient, but we do not characterize it yet. But we did some mutations, arginine and negatively charged residues to see proton transfer also, but the fluorescence stayed quenched.